Okay, let's get started. So once again, thanks very much for joining us today. We'll be talking about material handling and hopefully show you some solutions that can help you deal with some of those challenges. Just in terms of introductions, I'm Rob Shropshire and I lead the sales and marketing side of Origin. I won't be doing a lot of talking during today's session, apart from a short introduction, but it will be your point of contact moving forward if you do want to spend a bit more time exploring the solution that we're going to show today. I'm really pleased to be joined by Peter Norland from Algorics, and he'll really be going into the detail of the product today, but he's focused really on developing a product that's holistic, by talking to customers about what their challenges are and hopefully coming up with a solution that meets those applications. So we know each challenge can be very unique depending on the type of challenge. Might be related to a bowl feeder or conveyor system or chute or funnel. So I think today is just about exploring some examples and hopefully proving our ability to come up with a solution that would welcome the chance to explore your challenges a bit further later on. So to start with, I'll provide a brief introduction and then talk about what we think the opportunities are for using simulation to solve some of these challenges. I'll then briefly summarize what Algorics is before passing over to Peter to go much more in depth and explore some specific examples and talk about what those challenges are. We prefer the sessions interactive, so please do feel free to ask questions. Typically, we ask to save them towards the end, but Peter likes to be quite interactive. So if you've got questions as he goes through the demonstration, please don't be scared to put questions in the chat box. We can chat about it, explore it. So yeah, please do get your questions in. You can do that just by entering them into your chat box. So a little bit about Origin. So we've got about 200 customers. All of them are in the UK, focused on the manufacturing sector. I think what's really unique about Origin is that we are really focused on the design side and really advocating for using simulation much earlier in the design process. So to us, that means using simulation to actually drive the initial design, whereas typically we find that simulation is used perhaps towards the end of a design process where a lot of that design time has already been spent. So we think there are lots of benefits to sort of bringing that shifting left and doing it much earlier. We'll provide the local training and support here in the UK, and the product that we'll be showcasing today is from Algorics, and I'm sure Peter will give you a bit more background on Algorics and the challenges that they're trying to solve. All of the solutions that we provide, we think are relatively low cost, with a low initial investment compared to a lot of solutions out there. So we hope sort of whether you're small, medium, big, you can make use of the solutions, and we try and make sure that the technology is relatively easy to use and quick to train users on. So just in terms of the opportunities, you know, one of the main things for us is trying to differentiate yourself in the marketplace. Preparing for this webinar, many of you might got phone calls or emails from us. So we did speak to a lot of companies. Some were doing conveyor systems, some bowl feeders, some robotics, and what we found that very few were actively using simulation. The majority were using 3D modeling. They'd use something like SolidWorks or Inventor, or perhaps using 2D, which to some extent is of course valuable. A 3D model allows a customer to visualize what the production system might look like. It allows them to see how it might fit in their space. But what it doesn't do is actually help the customer to visualize and understand how you're actually going to solve their material handling challenge. So how their material is physically going to flow through your various systems. So you know, we think simulation actually provides evidence and allows you to properly test the dependability of a solution as opposed to just 3D modeling. Now, of course, you know that there might be some people on the call that say, well, we can do this, we can do it in the real world, we don't have to use computer simulation, and that, you know, is true. We spoke to several companies that for example, design bowl feeders, and their method would be just to throw some material in the bowl feeder, see what happens, and then sort of try it again until they came up with the perfect solution. And this is fine, but many people talked about, well, how long would this take? You know, if we needed to make a tweak and we needed to machine a component, how long would that take, both in terms of our design time, but also any cost in terms of materials or machining. The other thing to bear in mind is that physical testing is also something that you are very unlikely to do before you've actually won the contract or work, and that's with good reason. It takes far too long to do that. But how can we ensure then that we stand the best chance of actually winning the work in the first place? And we think that by using simulation to come up with some concept and prove the idea without necessarily spending hours or days or weeks coming up with a proposal is a sensible thing to do, and helps to differentiate yourself in the marketplace. The other thing is that some challenges are just simply quite tough to replicate in real life. We spoke to companies, for example, that did conveyor systems, and if they were just modeling some bottles going down a conveyor line, that would be fairly easy to do that in real life and see whether they might fall over and see how those bottles would flow through. But if you had a multi-track conveyor system with 2 or 3 different conveyors with all of those products coming in at a different speed, and you need all of those to come down to a central conveyor without bashing into each other and smashing, that might be more of a challenge, and that's something that simulation can help us do quite quickly. So in terms of summary, we think the opportunities are that you can differentiate yourself, and because of that, hopefully win more work. You can save time through not doing sort of lengthy trial and error exercises, and also reduce cost, and hopefully allow you to explore multiple designs very quickly, check the feasibility of a job, and deal with those more complex challenges. So one more slide from me, and then I'll pass over. What is Algorics as a product? We'll simply put, it's a suite of tools that's built on top of an existing 3D package, 3D modeling package called Ansys SpaceClaim. And this gives you all of the features you're going to need to create and amend geometry, but also import geometry from your preferred CAD package like SolidWorks, for example. So you can import your idea or your design, and then you can essentially run simulations to look at that material flow and to identify any issues that you might have with the design. And then you can edit that design on the model and then rerun that simulation to have a bit more of an iterative design process. I think what's interesting about this solution is that Algorics have worked hard to try and get you going quite quickly with a selection of templates. So templates for bowl feeders and conveyors and sorting machines, which is something we'll talk about a bit more as I pass over to Peter. So that's enough from me. I will be moderating the QA, so again, get your questions in, but hopefully I've set some context in terms of what we think some of those benefits are in using simulation. And I'll now pass over to Peter to start talking a bit more about the product. So Peter, over to you.
Thank you very much, Rob, and thanks for that excellent introduction. Let's see if I can just share my screen here. Let me know when it appears on your side.
Yeah, we can see the web page, Peter. Yeah.
Okay, awesome. So as firmly established already, this webinar is about Algoryx Momentum, and Algoryx Momentum is about material handling in factories. So it's a tool where you can design and simulate vibratory feeders, typically bowl feeders, conveyor systems of various kinds, and other like special purpose machines that do sorting and orienting, that kind of thing. I'll just hide that. And we like to split this overarching challenge of material handling in factories into 3 different categories. So the first one would be to move objects from A to B, essentially transporting material through the production line. So here we have things like conveyors, feeders, etc. The second one is to create order. This typically involves bowl feeders, special purpose machines, dispensers, and things like that. And the last thing is robotics and autonomous systems. So this involves control systems, sensors, mechanics for grasping, cables, suction cups, and more. And this third part here is like very much at the center of what Algorics is doing, but it does require a software called AGX Dynamics, which falls a little like in the outskirts of the topic for this particular webinar. But I'm thinking if there's time left at the end, then maybe we'll show some examples of this software as well. But today we will focus on these two things, and I'm going to show you how to solve like real practical problems in each of them. But first, so why does this matter? Basically, if you look at a factory, a typical factory, you'll note that things tend to change. It's like almost like a living system. You improve the throughput, you clear out bottlenecks in the system, you might replace machines with new ones. There might be changes to the product itself, which require corresponding changes in the production system. And these changes in the factory, they can impact the material handling aspects of the factory as well. And some of these changes, they add new constraints into the factory. And some of those constraints might be compounding over time as well, giving rise to like increasingly difficult material handling problems that require creativity and innovation to solve. I'm sure that at least some of you feel that this is a somewhat familiar picture. And then when it comes to creating order, we know that order can be quite expensive. It is often cheaper to transport a product in the form of like a bulk material. But that presents this problem of having to create order in the system when you need it, when you need to line up, for example, I don't know, the bolts that you've been manufacturing so that you can package them and process them further and so on. And many of these problems, they require completely unique engineering solutions that can be quite difficult to achieve. And some things that these three categories of problems have in common. So they tend to be quite valuable. They facilitate the production of a product, and that can be very valuable. And if the material handling solution fails, if it's not reliable, then that can cause some serious problems in the production system and incur cost as well. They can be quite difficult to solve because things move, and that makes things difficult. They tend to be like in operation 24/7, which means that everything that can go wrong in these systems eventually probably will go wrong as well. There tends to be a lot of like unique engineering solutions here. So if we look at bowl feeders, for instance, there are hundreds of thousands of bowl feeders in the world, and I believe that it's fair to say that almost all of them are unique designs for a very, very particular purpose. These systems can also be difficult to test in the final intended context of operating within the factory. And this is essentially the engineering challenge that we have decided to solve as well as we possibly can. And that is what Algoryx Momentum is about. And now I'm going to show you the actual software. We will look at a number of different models. First, I'll show you some like quick examples to give you kind of an overview, an idea of basically what the possibilities are. And then we'll focus a little extra on two models at the end. One is about a bowl feeder, and the other one is about a conveyor system. And as Rob pointed out before, you're very welcome to interrupt me at any time and ask me questions. Typically, when I show our software and discuss it with customers and so on, it tends to be a back and forth conversation that can take any direction. And that makes it quite exciting for me, and perhaps more meaningful for the person I'm meeting with. So I definitely invite you to ask any questions about the software itself, but also about the models that we're going to look at. So let's see if I can find the software. Okay, so I hope that you can all see this on your screen now. This is I'm not even sure what to call this machine, but it's if I run the simulation, you will see what it does. So I'm using just a laptop, and what we see now is the simulation actually like computing the physics of the system and animating it at the same time. But the purpose of this machine is to take this, incoming bunch of screws and output them on a straight, orderly line like that. So we have this escalator, and here we have a linear feeder as well to drive the system. And when I first got this model, this assembly, it didn't work at all. The bolts immediately got stuck here. There was a traffic jam here, and they tended to get stuck over here as well. And then I went through, I don't know how many iterations, maybe 40 iterations or something, design iterations, trying to find a dependable solution here. And I think dependable and reliable, robust, those kinds of words, that's really what I am aiming for, and I think what most of you guys would be aiming for as well. It's not so much about optimizing things, it's about making things work. And as I was searching for a solution, I changed this and that, and maybe I solved some problems, but I also introduced new ones. I solved some problems and discovered new ones. And over time, my solution became a little unwieldy, and I decided to start over from scratch again, and arrived at this solution that I just showed you. And it's a really clean solution, I think. It can probably be even cleaner and even better. But I think it's reasonably clean, and it's when it's completed like this, it probably looks quite simple, but there is some thought that has gone into almost every single detail of the design. So this piece here, for example, it was moved backward a little bit, or further downstream, to increase the probability of incorrectly oriented screws falling down on either side. We made the linear feeder narrower, iterated a few times the design of this piece, and so on. Okay, I don't want to spend too much time on this model, but I just want to give you an overview there. I think I'll close this now, but if you have questions that relates to this model, I can certainly open it up and we can go back to it later.
It's just a quick question, Peter. You mentioned that you're using a laptop. How powerful a laptop do you have to use for this to work?
I do have a new laptop now. Let me see if I can find the specifications of this one. There to that. My previous laptop was not even remotely this powerful. Sorry, let me just. Where do I find this? This PC. Is it maybe here? Properties. So these are the specifications of this particular laptop. So it's quite powerful, but you can get away with a fairly mundane PC, and the simulations run on CPU. So the hardware tends to be quite affordable, actually.
Okay, thanks.
Yeah, I would
If
say that
anyone's
the
got any
laptop
more,
on-
if anyone's got any specific questions, we can, you know, obviously send specs out if anyone's interested. Minimum spec, we can get that to you.
Yeah, exactly. I would say that this laptop that I'm using, it's almost a little excessive for this. It's very computationally efficient, this software. Okay, so here's another example. Thanks for the question, by the way. Don't be shy. And I'm just going to run this one right away. Okay, so here we have a conveyor, and as you can see, I'm not sure what to call them, the forks. They maintain a constant orientation, but obviously you can have other kinds of conveyors, bucket conveyors, for example, where the buckets might turn as they move along the trajectory. They can even be jointed, if that's a better representation of your actual design. So here we have some containers with some items in them. You can see that this light here is changing between red and green. And what you'll notice is that there's actually a control algorithm involved here. So you don't want there to be pile up here, because then the boxes will tip over and so on. So there are sensors that detect if this space is occupied and if there's another one coming in, and then pauses the conveyor belt when necessary.
Peter, just to interrupt you again, if you don't mind, just a question that's come in. At the top of the lift, what is moving the screws over into the linear track? And then there's sort of a sub-question to that. Can you set frequency and amplitude of the linear track?
Yeah, sure. So that's the previous model.
Yeah.
Let's close that one down. I think I'm done with this one, so I'll just leave it open. Why not? So where was that one? I think it's this model. Okay, so the question was about the linear feeder, is that right?
Yeah, at the top of the lift, what is moving the screws over into the linear track? And then can you set frequency? Can you set the frequency and amplitude of the linear track?
Yeah, excellent. So what's not been so apparent for you guys yet is the actual orientation of this assembly. If I just line it up better, we can see that it's tilting. So it's gravity that's moving them over like that. So I hope that answers the question. And the linear feeder, right now in this version, it doesn't vibrate. There is only, like we call it a surface velocity, so it operates a bit like a conveyor. But previously, I added vibration to it as well, so you can choose whatever you want. And I think when we get to the ball feeder example, you'll get a better sense of how that works. I figured when I was trying to identify a solution to this problem that by assuming that there's no vibration here, I would remove the disturbance of vibrations in the system, and thus increasing the risk of screws getting stuck here and there. I figured that if things were vibrating, then that would shake things loose a little bit more easily. So I was trying to make the problem a little bit extra hard for myself. while trying to solve it. But then when you're approaching a final design, then I think it's good to shift mindset and try to like really stress test the design and experiment with different scenarios and possibilities, and you would definitely run a simulation where the feeder actually vibrates.
Thanks, Peter. Hopefully that answers the question, but if there's any more follow-up questions, then send them over.
Yeah, that was a good question. Let me move this one over. Okay, so a final example before we go a little bit deeper into the ball feeder and the conveyor. So in this case, we have some bottles coming in, and there's broken glass in the model as well. So I'm trying to model a scenario where there's broken glass coming from upstream in the material flow, and we want a way to remove these broken pieces and allow the bottles to continue. This is moving unusually slowly now for some reason. It's because of too many models open or something. Let me check if it did something weird. I'll close these other models. So for some reason, it's very slow. It's typically almost running in real time. I don't know what's going on. But anyway, we have a hidden piece there. Let me just show what happens. So clearly we'll have a bridge here that I've hidden now, which allows the bottles to cross over, and it separates the broken pieces out. And this problem too required quite a few iterations to get right. And I arrived at this solution here. And again, it looks perhaps somewhat simple, but there's a lot of little detail that goes into this. For example, you don't want the bridge to be completely level with the conveyor belt because you don't want the bottles to trip on it. Also, you want to make sure that the bottles are, you can see that they're a little dispersed here. It's not like a super compact flow. But when they get to the bridge, you want to maximize the probability of the bottles making it across without tipping over. And one way of doing that is to slow down the flow right here so that they gather more closely and support each other. So that kind of the function is an integral part of the solution as well. And when it comes to the characteristics of the material flow, it can be like a perfectly ordered flow, or it can be somewhat randomized with the placements of the bottle. And it can be very much randomized, both in terms of placement and orientation. And if you need like even more, how should I put it, deliberate or specific characteristics of the incoming material, it can be a good idea to introduce the machine or the material handling system that was upstream of the system that you're interested in exploring and designing. So all of these examples that I'm showing you now, they're specific parts of a system, but there's no reason why you wouldn't be able to extend this further. So if we take the bowl feeder that we have here, for example, you can easily extend this model with maybe a linear feeder that brings the material into the bowl feeder and so on. Okay, so let's look at this model here. So we have incoming material, and this material can have any kind of shape that you might want. So there's no limitation as to whether it's convex or concave or whatnot, and it's the actual geometry of the parts that that drives the behavior here. And quite quickly we discover this issue. So where does that come from? Well, it has to do with this trap over here. So it allows these ones to get through, and then they get stuck here, of course, which is not what we want, and it's quite bad because it begins to interfere with the product that's like further down in the bowl. And we can also notice how the bowl is starting to fill up, and there's starting to like be enough product in here so that just the sheer number of parts begins to interfere with the performance of the device itself. So how would we go about solving this problem? Well, we could probably do a number of different things. We could maybe add something over here, change the geometry of this part, perhaps. Maybe make this section a little narrower. Something that would, increase the probability, or basically make it certain that those incorrectly oriented pieces would fall off. One solution is to, let's see if I can find it, is to add something like this. This rod here. And this can be, like in this current design, it's attached to something that's, comes from outside of the vibrating bowl, but this could also be something that is attached to the bowl itself. We could also maybe make changes to this geometry here, if we like. Maybe we want to pull it up or down, make it narrower, and so on, if we think that's a good idea. There's like plenty of opportunity to experiment and step outside of previous experiences and previous, things you might find in textbooks and so on. So let's hope that we get a little better performance in this example. Okay, so if we zoom in a little bit, we see that the bowl is actually vibrating, and that is what drives the motion of the product. And you can adjust the frequency and the amplitude of that vibration to match what you would have in real life. And in this case, it's a bowl feeder, so it has a combined vertical vibration and rotational vibration. If it's a linear feeder, then it would just be like a vertical and longitudinal vibration. So you have plenty of control there to steer that. And as Rob mentioned before, we can think of this model, this document that we have here, as a template. We call it the Vibratory Feeder Lab. It's a place where you can easily import your designs, bowl feeder designs, whether you work in SolidWorks or some other software. You can easily bring it in here, and all you have to do is to place it correctly and specify how you want, like the parameters of the vibration, essentially, and then the inflow and outflow of materials here, and you are good to go. And as I've hinted at already, since we are inside of SpaceClaim or Ansys Discovery, we can very easily go in and edit the geometry, change the placement of various traps, change their geometry. We can create entirely new geometries in this environment as well. And this is very much like a process of trial and error. I would say it's, in my experience, it's very rare that you can sit down and just conjure up in your head a good solution for a bowl feeder and then it works right away. If it's somewhat a new product that I haven't worked on before. So it's a good idea to like truly embrace that interactive trial and error kind of workflow, and you will learn to not fear things going wrong and fear failure. Instead, you will learn to appreciate them, because every time your design fails, it is an opportunity to learn something, and sometimes to learn something profound, like a principle that you can introduce in your design. And I really like that. I think I want to like truly avoid, fiddling with parameters and making minor adjustments and tweaks and try to like optimize towards something. And instead of that, I try to think in terms of conceptual optimization. I want to identify a set of principles, and if I implement those principles into the design, I know that the solution will be intrinsically robust and dependable, even if there are variations in the precise design or variations in the context in which the machine operates. I mean, we know that the coefficient of friction, for example, can vary from place to place and even from day to day. In some factories, there's a bit of oil mist in the air that can have an impact on friction, which means that you might design your bowl feeder in in your lab and test it extensively, and then when you install it in the factory, there is something unexpected about it that causes it to malfunction.
A couple of questions, if you don't mind, please, Peter. The first one, which came a little while ago, was: is there a limit on material bodies, or is that just sort of dependent on your PC?
So we are going to introduce a bit of a limit to the number of bodies. So depending on what level of what license you decide to invest in, basically. So the license level that is intended for this particular use case of material handling in factories. Currently, we plan to implement a limit of up to 10,000 bodies in a simulation. If you go to the tier above that, then there's no limitation whatsoever other than the hardware that you have available.
Mm-hmm.
So if there are systems where there's maybe millions of bodies, you will need a powerful computer and you need a hefty hard drive to store all that data.
Mm-hmm. Okay, thanks for that. I've just a second one. How is the part or component model created? Is it a step file import, or is it designed directly in the software each time? And then I guess a sub question to that is how detailed can the part be? Another limitations in terms of the detail of the part. So yeah. I'd imagine it's either or. You can create the component in our software or import it, but I'll let you sort of elaborate on that.
Yeah, that's exactly the case. You can create any imaginable geometry inside of this environment directly, but you can also import parts from virtually any 3D CAD software, which is a good thing if you're, maybe your clients use a different CAD software than you do, then you can import a step file and so on. And once that is imported into the model, you can continue to edit that geometry right away as if it were a native part. Yeah,
just to reel off a few: SolidWorks, Inventor, AutoCAD, MX, CATIA, step files, IGES, all of those can be imported directly into the software, and then you can work directly on the model, which is great for design exploration because this is a direct modeler. So if you're dealing with a customer's file and you're importing a part, you don't necessarily have to understand the structure of the tree and the parametric makeup. You can just get in there and play around with the geometry. So yeah, either or. Hopefully that answers your question. Ask more if we've not answered it. Peter, I will just give you, we've got it's 2:45 now. So I don't know whether you want to perhaps move on to the conveyor example. But yeah, if we've another, just ask questions as we go, and then we won't need a big time for Q&A at the end. But if you sort of go for another 10 or 12 minutes, Peter, and then we can start to approach the wrap up.
Awesome. Thanks for the head up.
No worries.
Excellent. And regarding the question about if there's any limitation to the complexity of the parts, the geometrical complexity, there isn't really. If I stop this simulation quickly and just to visualize the contact constraints that we have in it. Oops. I discovered that there's something not so good over there. A bit of a collision there. But anyway, so these orange markers, they indicate that we have contacts. And contacts, they are among the most computationally expensive aspects of these simulations. So if you have tons and tons of contacts, then that will slow down your simulation. And basically that's the only drawback of having extremely complex shapes. On the other hand, having an extremely complex shape doesn't necessarily mean that you get a lot of contact points either. Okay, I'll close that one down. And then the last example here. Okay, so let's imagine that we find ourselves in this situation in a factory where we need to split a single lane of incoming material into two separate lanes. And there are, Traditionally, there are different ways to do this. It doesn't seem entirely uncommon to have like an active system that senses when an incoming senses each incoming bottle and maybe pushes every other one into a different lane and so on, or using some kind of air nozzle to do that. What I want to do and what I want to aim for generally is solutions that are as clean and simple as possible. In this case, I want to minimize the space that is required for this forking event as well. I want to make sure that the solution is intrinsically robust, like basically fail safe. And in this particular application, we want the output of material, the two lanes that come out, to have a consistent, compact, and regular flow to it. And this is the initial design. And there's a bit of a divider in the middle, and we see that it kind of works for a little while, and then it clogs up. And even before that, we could see that it was a bit irregular, a bit erratic like that. And I have, I'm going to try to solve this problem now and arrive at a better solution. And before I do, I want to point out that I promised myself that I wouldn't practice working on this example, because I want it to be like an improvised thing, and I want to run into issues that I have not anticipated, and try to kind of capture some of the experience that you get when you're using this software. But one thing I'm thinking of, and if you do have any suggestions for me, then just let me know, and we can try that, hopefully, if it's not too complicated. But this piece in the middle is clearly a problem. So I'm gonna, like, right away try to make that more narrow. I've solved this problem once before, just so you know, so if I fail completely now, then I do have that backup model that we can look at. So I'm just going to make it a little bit more narrow here, and move the conveyors along with that. Oops. And just say 40 millimeters. By the way, so there are lots of really useful shortcuts and stuff in SpaceClaim. So if you're not used to this environment, you would probably go over to the Design tab and find these different operations that I'm using over here. But I prefer to just stay in the Momentum tab and use shortcuts to activate those different tools. So if we simulate this again, see that they're coming in, and on the first conveyor, there's quite generous spacing between those vials, and they come in at a certain velocity, and then they reach this conveyor, which has a lower velocity, so that the flow can become more compacted, and the bottles start pushing against each other, and that in turn causes the flow, or this lineup, to become unstable, so that it starts to divert off to the side. So that's part of the initial idea. It works a little so and so. We still have this kind of random behavior. Let's try something more. Let's make this area here a little narrower. I think that can help us just tidy things up a little bit. So I don't know how much. Let's say 40 again. And same thing over here. And now I'm just manipulating these objects that we already have in the model. I can create new ones if I want to. I can remove parts if I want to do that as well. I can make copies and so on. So it truly is a very interactive and fluid environment for solving these problems. And for me, it's always a learning experience, and it's so convenient that I can, just run simulation after simulation. I can stop the simulations. I can zoom in if I make changes. I can, simulate it again with this precisely the same, external factors, so that I can understand, the impacts of the changes I made. And I think that's also a super valuable thing here, that let's say that you're watching a video of a system, a conveyor solution or something, and maybe it doesn't work very well, and you look at that video, and that will certainly give you input and insight and information. But if you're able to go in and make changes to that system and immediately see what those changes resulted in, you will start to build this deeper intuition about cause and effect in the system, and you can generate more principles and theories for what's important here. And I think that's pretty cool. So I see that we're starting to run a little short on time. So I think I will try to move forward a little more quickly. I'm going to remove this divider altogether. It feels like maybe we need it there, but I'm going to remove it, and I want to try to arrive at a design that relies entirely on that mechanism that I mentioned before, where the bottles would kind of line up closely to each other and then veer off to the sides because of the physics in that system. And if we succeed in that, it will probably be a quite reliable solution, because we don't have that divider that could cause any kind of traffic jam in the system. I think, what else do we want to do? We can move these a little closer to each other still. So maybe another, I don't know, I'm going to say 5 millimeters. And we can simulate this again. Okay, now they're just perfectly lined up like that. What if we reduce the velocity of these conveyors? Properties, and say we reduce it to 100 millimeters per second instead. What I'm thinking now is that they will slow down even further, so they will be even more compacted. Yeah, and it kind of almost works. They're starting to separate a little bit. I wonder, what if we, let's say, my initial idea with this section here was to, as a first increment, reduce the speed from the initial incoming velocity to something slower, and then the third stage would be the final velocity of the bottles. So this is like a middle step so that the bottles wouldn't tip over. But I think I'm gonna remove that and just be a little more, I don't know, a little more brutal or something, and have the remove that transition and instead take these two conveyors and move them up to there. Right away, we can move those two just to make things look a little more tidy. Okay, so let's try this. It's getting there. It's like when it begins to, it takes a few moments before it becomes unstable, and then it begins to separate a little bit. I see that we're running out of time, so I'm gonna take a leap from here over to the model that I arrived at before. So it looks quite similar. So this is what we arrived at, and this is what the design I made earlier today. And I'm just going to run the simulation. So you see that we have this system now where there's no obtrusion whatsoever. There's like basically nothing that can cause it to jam. We can use a quite massive, we can have a massive throughput in the system, and it still manages to process that. There is no like active mechanism involved at all. And you can see how this instability that I was talking about, it's propagating upstream. So they're already beginning to separate up here, which is perfect. And we could probably make this solution even more compact if we wanted to. Okay, so that's, I say that's it. What do you say, Rob? Do you have any
Thanks.
more? Are there more
yeah, thanks very much for going through that. I think we've gone through quite a few different examples, and I think what we're sort of trying to perhaps get at is there's not a sort of silver bullet, as it were, but hopefully what you've got is a toolkit that will allow you to try things and come up with solutions really quickly. There's not sort of a formal summary per se, but obviously if you do want to look at it in more detail, then there are trials available that we can make available to you, or you might find it more useful to explain what you do day to day and maybe explain some of the challenges that you're having, and we can review that in a bit more detail with you. You'll also get the recording as well after the session. There's one question before we wrap up, Peter, just because we are tight on time, but there's one question that's come in. Yeah, again, it might be a difficult one to answer. How easy is this software to learn? You know, how much training do you think it might require? So yeah, I don't know if you can have a quick stab at that question before we finish up.
Yeah. So if you're reasonably comfortable with 3D CAD from before, I think that I know that it doesn't take much time at all, maybe an hour or two, to start to feel comfortable with, you know, how you do different things in this environment, where you find the different buttons and settings and so on. But what it ends up like, what ends up being the main challenge in using the software is the engineering aspect of the problems that you're working on. In the end, being creative, coming up with reliable solutions, figuring out ways to test them to make sure that they're dependable and so And what we've talked about today is just, we're just skimming the surface. But there are really good ways to shift focus when you're designing these things. You can set up your simulations in a way that you can quickly iterate and problem solve. And then when you have a more mature solution, you can run really, really long simulations and test your design for hours and hours and hours of physical time to make sure that it's robust.
Thanks very much. So I think that's that will probably be it. We're just over time now. We've got your details for those of you that have attended. We will follow up, see what you thought, answer any extra questions that you've got, and also perhaps you can share some feedback with us about what you thought. So for everyone that attended, thanks very much for your time. We do appreciate it, and hopefully we'll look forward to speaking with some of you in the future. So I'll close the session now, but thanks very much for your time.